Welcome to your ultimate exam survival guide. Today, we're going to transform the complex, and let's be honest, sometimes super frustrating world of beam reactions into a crystal clear, repeatable solving pattern. If you've ever stared blankly at a structural analysis problem, just wondering where to even begin, well, this explainer is built specifically for you. Let's dive in.
Here's our roadmap for today. We'll hit 5 key steps: the master equilibrium concept, decoding beam support restraints, beams and load conversions, the repeatable solving pattern, and finally, exam prep and pitfalls.
All right, let's jump straight into Section 1, the master equilibrium concept, which is all about setting our mathematical goal.
Before we can calculate anything, we absolutely have to understand the fundamental physics of why a structure doesn't just, fall down or fly away. In engineering, we're usually dealing with a coplanar, non-concurrent force system. Now, that's really just a fancy textbook way of saying we have forces acting in the same two-dimensional plane, but they don't all intersect at a single point. So, what does this actually mean for us? For perfect equilibrium, 3 conditions absolutely must be met. The sum of all horizontal forces, vertical forces, and rotational moments must perfectly cancel each other out to exactly 0. That right there, that is your ultimate mathematical finish line.
Moving right along to Section 2, decoding beam support restraints, or as I like to call it, the handcuff analogy.
Now that we know the math, let's decode the physical environment. Think of structural supports literally like handcuffs. Whenever they restrict a specific type of movement, a reactionary force is instantly born in that exact direction to push back. Look at a roller support, for example. It allows the beam to roll horizontally and pivot, right? Because it allows that movement, 0 reactions there. But it totally restricts the beam from moving vertically downwards. Since it stops that downward translation, bam, it creates a single perpendicular reaction force pushing straight up.
You are definitely going to want to memorize this matrix for your exam. It summarizes exactly what happens at every connection type. Simple and roller supports restricting just one direction, yielding one reaction. Hinged, or pinned supports, restrict translation in both horizontal and vertical directions, so we've got to resolve them into 2 reaction components. And then we have fixed supports. These are the ultimate handcuffs. They lock down all vertical translation, all horizontal translation, and all rotation. That means they develop a horizontal reaction, a vertical reaction, and an internal restraint moment.
Okay, Section 3, beams and load conversions. Time to prep those variables. So, we know how supports push back from the bottom, but what's really interesting is how we handle the messy, real-world action loads pressing down on our beams from the top. Textbooks love perfectly neat single arrows, but in reality, weight is spread out. We deal with uniformly distributed loads, UDLs, and uniformly varying loads, UVLs. To actually apply our equilibrium equations and make the math easy, we use a neat conversion tactic. We turn these spread out forces into clean, concentrated point loads.
Check out this uniformly distributed load acting over a specific section of a beam. It's basically a solid, uniform block of weight. To convert it, we just take the magnitude of the load, which here is 20 kilonewtons per meter, and multiply it by the physical length of the span it covers, which is 3 meters.
It's not simple. 20 times 3. This quick math dramatically converts that bulky 3-meter wide load into a single 60 kilonewton concentrated point load. And remember, for a uniform distributed load, that point load acts right dead in the center of the span.
Now what about a uniformly varying load? You know, the one shaped like a right triangle on your diagram. The tactic shifts just a little bit here. This represents a load that steadily increases in intensity from 0 at one end all the way up to a maximum at the other. To find the total point load for this one, we literally calculate the area of the triangle. 1/2 times the base length times the height magnitude. And then, and this is absolutely vital, guys, we place that resulting point load precisely at the triangle's center of gravity. That is always 1/3 of the way from the heavy, flat side of the triangle. Think of it like trying to balance a slice of pizza on your finger. The center of gravity is always closer to the crust.
All right, Section 4, the repeatable solving pattern. This is your free body diagram master recipe.
We've got all our ingredients prepped, so here's your foolproof, step-by-step exam procedure. First, confidently state your 3 equilibrium conditions right at the top of your page. Second, draw a totally liberated free body diagram where you resolve any inclined forces into vertical and horizontal components and convert your uniform loads into point loads. Third, systematically calculate your unknown reactions. Let's actually see what that looks like in practice.
Let's watch this build conceptually. Here we have a continuous beam resting on hinged supports. Your very first calculation step: identify every single action force pressing down on it. If you add UDLs or inclined forces here, you'd mathematically convert them right now using our formulas into clean downward and horizontal point loads. Next, literally erase the physical supports on the bottom and swap them out for actual reaction arrows. Remember, a hinge support gets 2 arrows, a vertical and a horizontal. Bam! Now you have a pure mathematical diagram. To finish the calculation, take moments about one of the supports. By picking a support as your pivot point, the distance for that specific reaction becomes 0. And anything multiplied by 0 is 0. This magically eliminates it from the equation, allowing you to easily use basic algebra to isolate and solve for the other unknowns. It's a real game changer.
Almost at the finish line. Section 5. Exam Prep and Pitfalls. Let's secure that grade. That right there is the magic of the free body diagram method. But to ensure you execute it flawlessly, use this summary table to instantly recognize how different beam types dictate exactly which support restraints you've got to calculate. A simply supported beam just has basic end supports. A continuous beam spans 3 or more. A cantilever? It's fiercely fixed at one end and totally free at the other, meaning you absolutely must account for that fixed restraint moment. And a propped cantilever mixes them up. Fixed at one end, simply supported at the other. Instantly recognizing the beam type tells you exactly what reaction should be on your diagram.
Finally, let's talk about lost points. Consider this a warning label for your next exam. The most common pitfalls students make under pressure are forgetting that hinged supports require resolving into both horizontal and vertical components, totally misplacing the center of gravity when converting those tricky triangle UVL loads, and finally, completely missing the restraint moments when drawing fixed supports. Keep this checklist in mind and double-check your diagrams before you even touch a calculator.
You now have the exact sequence to break down any static equilibrium problem. Define your equilibrium goal, decode your supports into arrows, simplify your loads, and systematically solve the diagram. So now that you're armed with this repeatable solving pattern, how are you going to deploy it to completely crush your next engineering assignment? Thanks for hanging out with me on this explainer, and happy calculating.